Again, welcome to Research Methods in Computers and Society. This is CS312 class. So in these lectures, we're going to cover how to analyze quantitative data, which is our Unit 10 lectures. And also it covers chapter 10 of our course textbook, Analyzing Quantitative Data. So our main objective in these studies is we are going to learn why statistics are used in research methods. And also we are going to conduct univariate analysis. A univariate analysis means we have a data set with only one variable. We're also going to describe the various ways to graphically represent data. Also, we are going to explain the measure of central tendency. Also, we are going to explain the measure of dispersion and also conduct bivariate analysis using correlation coefficient concepts and also regression analysis. So we can see that from the objective of these lectures, it seems we are doing the review of statistics. All the topics here and all the objectives here again covers statistics. So analyzing the quantitative data, here we start with the definition of statistics. We say a branch of mathematics called statistics is used to analyze large amounts of data. And also statistics uses mathematical logic to interpret phenomena and also draw conclusions about accumulated data. First, we know statistics, we have two main branches, the descriptive statistics and inferential statistics. Also, we have probabilities. Most statistics textbook, you always see descriptive beginning chapters, probability will be the second, then the last chapter will be inferential statistics. Now, within inferential statistics also, we have the parametric testing and also non-parametric testing. Choosing what method we should use will be based on the type of data we have. So we know in statistics, we have four major level or different types of data. That's the level of measurement of a data. So we can start with the nominal data. The nominal data or a categorical, sometimes we use the term categorical. It's a data that we can not do any mathematical operations on. The only mathematical operation we can do is counting, is to count. So example, we may have a data set about patients with a specific disease, let's say patients with a cancer. So we may have the variable for cancer, yes or no. Now, if our values for that variable is only yes or no, there's no way that we can find the average value of yes or no's. The only thing we can do is counting. Or if we have a variable with values of, let's say, true or false, or the color of the textbooks, yellow, blue, green. These are all test words. We cannot do mathematical operations on. So if I'm doing a test and I have this type of data, I cannot, this data is not a quantitative data. We may use another term, which is qualitative data, but also we can say categorical or nominal data, which means we can do only non-parametric tests. We can do a quantitative testing. So the second one will be the ordinal. Ordinal means the data is in order. Let's say we have cigarette smoking, light smoker, average smoker, heavy smoker. Or we have NBA League, New York Knicks is one, LA Lakers is second, Brooklyn Nets is third. So they are in order. So ordinal data, we can do only relational operators, greater than or less than. So we can say, okay, Charles Edeki smoke more than Peter Williams or any. So that's ordinal data is in order. Then the last part is the quantitative data, which we have the interval and ratio. The difference between interval and ratio is that with interval, 0 means something. So example would be a temperature variable. When the temperature is 0, it means it's very cold. But if I have a bank account and my bank account balance is 0, it means nothing. I don't have no money. So bank account variable will be ratio. Ratio 0 means nothing. Interval 0 means something. But both of them, we can do mathematical operations. Normally with the interval, we can do greater than, less than, counting, and also we can do addition, subtraction. Then with the ratio, we can do all the possible arithmetic operation. So we can see that again, here we talk about 4 different levels of measurement of data. So choosing the correct statistics method to analyze the data will be based on the type of data you are trying to analyze. So here, statistics, also quantitative data, can establish relationship between variables. And we are going to discuss about this using the correlation coefficient and also regression. So relationship between variables and also attempt to predict future behaviors or relationships. So we start with the univariate analysis. Now, if I'm doing if I have a univariate analysis, it means if I'm doing univariate analysis, it means what? My data have only one variable. So if I have a data with only one variable and I'm doing univariate analysis, it means I cannot do a correlation. I cannot find a relationship between 2 variables because it's only one. So again, as I mentioned earlier, the type of data we have will determine the type of techniques we are going to use to analyze the data. So we start with the univariate analysis. The first thing we can do is the descriptive analysis, which is very important. Descriptive analysis allow us to understand the data. For example, we can know the mean, median, mode of the data, the central tendency. We can also try to understand if the values in the data set are the same, or they are very close to each other, or the variable is very high, So which means we can find the standard deviation or the variance. If the standard deviation value is very big, it means the dispersion or the variation of the data is very large. So for example, I have 3 values in a data set. I have 6, 7, 8. And I have another data set with 3 values. This time is 16, 40, 100. 16, 40, 100, standard deviation will be higher than 6, 7, 8 because 6, 7, 8 are very close. Let's say we have a third data set with 3 values again. This time all the values are the same, 7, 7, 7. Now, if all my values are the same, it means the standard deviation will be 0. So again, this is descriptive statistics. We try to find the central tendency of the data set. We're trying to see how the data varies, the dispersion of the data. And also sometimes the location of or position of maybe 25%, 50%, 75%, and that's where we find the quartiles. So those are the descriptive analysis. Inferential analysis, normally, again, that's why the key word is inferential, is to make some decision. So inferential analysis is we use a sample. When we use the sample and we get the result, we apply that result on the whole population. Now, if I want to do some studies in New York, the population is 10 million, and I need to do these studies to apply the decision to all the 10 million people. Well, if I need a perfect result, then I should take the data. I should collect the data of all the 10 million people, but that is impossible. First, it will consume a lot of time. And secondly, it will be very expensive. So in this case, the best way to do this is to collect a sample, maybe 1,000, 2,000 out of 10 million. Then I will do my analysis on the sample. The decision I will get, I will infer it make it to the population. So we're going to, that's inferential statistics. Then go use a sample, do your work, finish, then apply the result to the whole population. So this means we have to be very careful. The method we use to collect the sample from the population is very important. We want to remove or minimize the biases in the data set, the errors in the data set that is in the sample. So also in statistics, we have different techniques of collecting sample, again, based on the type of studies you want to do. So let's say I want to do a studies that I need 20 samples. I don't care whether they are male or female, just 20. So I can do a simple random sample, which means everybody have equal chance of being selected. Now I want to do another studies. By this time, I need exactly 10 male, exactly 10 female. So this means I can do cluster sampling, which means I may collect a sample for only male population, then go for the sample for only female population. So again, we have different types, different ways of collecting samples. So first, we start with the frequency distribution tool in statistics, which is part of descriptive statistics. Frequency distribution normally make it possible for us to organize our data to be organized. So for example, I have a data set about patients with some specific disease, and also I'm taking their age, the age category, and based on the disease. Now, if I have over 10,000 patients and they are not organized, we just have them in our database system. Now, if I want to know a specific category of age, it means I have to go through all the lists of the 10,000 patients. Maybe in a database, we organize this data in terms of patient ID or the patient last name. So we sort it by last name in order A, B, C up to Z. So which means we have to go through and look at the age category we are looking for. Now, if I can create a frequency distribution by organizing this data based on a class grouping, which will be on the age. So I say, okay, the age between 1 to 10, then 11 to 20, 21 to 30. Then I'll count all the patients in each age category and then put them in the frequency column. So the first column of the frequency distribution table will be the age groups. Then the second column will be the total number of patients we have in each age. So this will be very easy for me now. Next time, if I was asked, so again, next time, if I'm asked about a specific age category, I can just go through again the frequency column and I will know the number of patients or the number of patients that have that specific disease in that age group. So again, frequency distribution is used to organize our data, easy to again access any tally or any category of other product, patients, etc. in the data set. So here we say frequency distribution can illustrate the key characteristics of participants in your sample. An absolute frequency is the number of times an event or instance has been repeated. So that will be the total tally. I have 27 patients, 27 patients that have disease A. I have 100 patients that have disease B. Or the age group, between 10 to 20 age group, we have 7 disease A. Between the age of 40 to 50, we have 0 disease A, etc. Also, we have a cumulative percent, which will show the collective percentage of categories together. So an example will be the percentage of participants who have more than a college education. Also, we can do another tool, and this time it's a graphical representation of data. So we are going to use a graphic tool in statistics to represent our data. Then normally we have a word that says that a picture is worth more than 1,000 words. Now, if I have a data set and I'm able to represent it using graphics or visual representation of the data, I can see the pattern in the data so easily because it's more or less like an image. So in statistics, we have different types of graphs. For example, the bar graphs, histogram, scatterplot. Scatterplot is normally used if we have two variables and we want to find a relationship between them. So we're going to have X and Y, and we can see the pattern of the data. The scatterplot is almost same as line graphs also. The only thing in scatterplot, the points are not connected together, but with line graph, the points are connected by a line to each. So we start with the bar graph. Again, why do we use, as we said, why do we use graphs in research, other results or research work? Okay, so again, we are talking about the bar graph. So this normally use the vertical bars to represent each variable being steady. So the longer bars, of course, we have more frequency or higher frequency, while the shorter bars, we have low value, lower frequency or lower tally, total tally. So this is an example. Let's say we are doing some studies about race and ethnicity. So when we collect our data, we find out that the longest bar is the number of Caucasians we have. So we have over 1,500 Caucasians. The second is African American. We have somewhere around 400 African Americans. And then the third is Hispanics. So Hispanics is around 300. So again, the bar chart is normally used when we have at least more than 1, 2, 3 categories of values that we want to represent. So in this case, we have a variable, let's say a variable named race. In the race, we have 3 possible inputs or results. So we can represent it as a graph. Histogram also is almost the same as a bar graph, but there shouldn't be no space between the bars. And normally histogram, we can derive an histogram from frequency distribution table. So we have the class label. The class category of a frequency distribution will be our X value, which will be our horizontal. Then the frequency will be our vertical. So here we say they are related to bar graphs and used for quantitative variables, where categoricals are normally related to each other. So the bars are connected. You can see the bar chart, they are not connected. Bar chart also can be used for quantitative data or qualitative, it doesn't matter. And an example here is for qualitative because we have Caucasian, African American, Hispanics. This is a nominal data, qualitative. But we can also use it for quantitative. So bars are connected and you can see how each category relates to all other categories. So this is an example. So now if I have a frequency distribution, my class, first column, the class category will be hours per day watching TV. Then the frequency will be my second column, and that's the Y. So let's say from 0 hour to 1, the total tally is around 100, almost like 120, 140, the first bar. Then we have second class in our frequency distribution table. which is from 1 to 2, which will be around 300. So again, we can convert our frequency distribution to histogram. The class category will always be the x-axis, and the second column, which is always the frequency or the total tally, will be the y-axis. We can also use a line graph. A line graph, as we said, is almost same as a scatter plot. At least we need a minimum of 2 variables, and the line graph can tell us the relationship between the 2 variables based on the direction of the line. So a line connecting points in a distribution, useful in showing 2 or more categories. Also, it's useful in demonstrating relationship between variables. So the horizontal axis will be the x, the vertical axis will be the y. So if I'm doing some work, let's say I'm doing some research, and this is my graph, I want to find the relationship between TV advertising expenses and also the income generated or the sales revenue. So our sales revenue is our y-axis, expenses is our x-axis, which is the TV advertising expenses. So we can see the pattern of the graph here shows that we have an increasing order as the total expenses going up, which is going towards right, is increasing. Same thing, our revenue or sales increasing because it's going opposite. To the right of x-axis is increasing, and direction of going up is also increasing in sales. So this data set will tell us that there's a positive relationship between advertising expenses and revenue generated by sales. Also, most importantly, we need to consider the ethical issues of representing the data. We want to avoid manipulating the graph to make an impact on an audience. This is normally done by politicians. They can change the scaling of the data, and the pattern of the data will not be seen well. If the pattern is not a good, it's a negative pattern, then you want to hide it or lower it. To lower the pattern, all you need to do is increasing the scale. So for example, consider the scaling of your axis. Look these two. These two graphs, the data is the same. But the first one, we can see that there is no pattern. It seems like everything is constant throughout. There's only a slice. The reason why, yes, because the y percent, we can say that the scaling is too big from 0 to 20, 40. With the values we have is less than even 20. So why do we start the scaling from 0 to 20? So we make the scale very big so that we make our graph very small and the pattern will get lost. But when you look here, you know the values are less than 10, even up to 5, less than 5 even. So we start with 0 to 0 0.5 to 1, 1.5 to 2.5. So the interval is 0.5, 0.5 up to 5. So the scaling is very small, so we can see the pattern very big, where it's increasing, where it's decreasing, everything. But when we have a highest value is less than 5, and we start the scale from 0 to 20. Then it seems like we want to hide everything. So yeah, the first one, we are hiding the pattern by increasing the Y scaling. And the second one is the perfect. So two graphs on the same variable but different scales also we can see. The scale, you see when the Y scaling is very small, we can see the difference of the two. But when the scale increase on the Y axis, you can see the scaling of the two items, the bars also decrease. We had, so if we increase the scaling more, you will see that the bar will be decreasing. We also have what we call the pie chart. Pie charts are very common in categorical data, and also if we have large variables, different types of values, we can represent it by using a pie chart. So here we say the visual representation of a variable's distribution that can be impact on audience. So it works best with categorical variables, as we said, and also avoid overcrowding the pie chart. So this is an example. Here we have 3 or 4 different sections, and 3 different sections. The first, we have a great deal, only some, hardly any. So hardly any is the dark color. So this is a categorical data. So next we move to the measure of central tendency. Now we are trying, the first thing we do in statistics is descriptive. So far we're still doing descriptive. So we start with the frequency distribution. Frequency distribution is a tool we use to organize our data. We didn't do any calculation, just to organize our data so that we can know each categories of values, how many percent we have or how many quantity we have. Then we can convert that frequency distribution to histogram or use any chart to visually represent the data. So we talk about the line chart, scatter plot, the pie chart, column chart, histogram. These are all graphs that we can use to represent our data. Now, when you represent the data in a visual way, it's more easy to capture the pattern because it's kind of a picture. A picture word worth more than 1,000 words. So those are the 2 techniques we learned so far in descriptives. This frequency distribution table to organize our data, graphs to represent our data visually. Now the third step is how to measure the central tendency. This is very important, especially we have a quantitative data. We want to know the middle, the average of all the data. For example, we have a student, 40 students taking exams. After we grade finish, sometimes it's good to know the average of the whole class. That will tell you in general how the whole class did, not how each individual student did. So we can find a mean, median, mode, and the mode always can be more than one. We have unimodal, means only one mode. Bimodal means you have 2 modes. 2 mode means I have a data set and 2 of them have the same highest frequency. Mode means the highest frequency or the most frequent numbers. Media is the middle point in a distribution. Then the average will be the mean. Here we say average is sensitive to outliers. What this means is, for example, we have a village in upstate New York, and the population of the village is only 10 people. 9 of these people are not working. But fortunately, Bill Gates live in that village. Bill Gates make over $200 million a year. And now they say I should find the average of the salary of the 10 people. So I'll write 100 million if Bill Gates make $100 million a year, or let's put it $1 million a year. But I'll get 1 million plus 0.0 9 times. So the total will still be 1 million. Then I will divide 1 million by 10. Wow, that means average salary for that village is $100,000 a year in a very small village. So we see this small village with no big companies, nothing. Average citizen make $100,000 a year. While in a big city like New York City, the average salary is around $42,000 a year. I would like to move to that village. When you move there, you'll find out that there's nothing there. But because of the outline, so that is the outline. Outline data is a data that is very large or very small. Because Bill Gates lived there and he's a super rich man, it makes the average salary for everybody high. So that's why normally in labor forces or even labor and also real estate business, we don't use the average mean salary or cost of a house. We may use the median. If I'm looking for the median of the income in that village, it will be 0, because the median means I have to arrange all the values in increasing order, sort it in increasing order. So I'll get 0 all the way to the ninth 0, then the last will be 10 million or 1 million. Then I'll take the middle value. Since I have 10, the middle value will be 2, but still both of them are 0, 0. So 0 plus 0 divided by 2 is still 0. If the number of values you have is even number, it means you're going to get 2 middle values. So you take 2 middle values and find the average of it. If it's a odd number, then you take only 1 middle value. So median is very good. It's not prompt or sensitive to outliers, but mean is. And also we have mode. Mode is good for qualitative data. So you count the highest tally, most frequent numbers. So as we said earlier, we have unimodal data set means we have only 1 mode. We have 1 value, which is the highest frequency. Or bimodal means we have 2 variables that have the same amount of highest frequency. Or multimodal means we have many, 3 or more. The next will be the measure of variability. So this is the measure of dispersion, how the values of the data set varies. Now, if the data set or their data is the same, the value is the same, then we are going to get a standard deviation of 0. So normally to measure the variability of a data set, we find the variance or the standard deviation. If the standard deviation is 0, it means all the values are the same. If the standard deviation is close to 0, it means the difference are not too much. But if the variation is very high, the standard deviation will be a very high value. So here we say when numbers in a data set deviate from the center value, the data set has a lot of variability, which also we can use the term heterogeneous. Now, when the numbers don't deviate from the enter value, then the data set has a low variability, which is homogeneous. This is one measure of variability. We can use the range. The range will be the difference of the maximum value and the minimum value. So that tells us the range of all the values. If the range is 0, it means the minimum value is the same as the maximum value. We can also use the quotas to measure variability. So here, normally the quota, that's why it's called quotas. We divide the data set into 4. But actually we find the 25%, 50%, and 75%. So we only have Q1, Q2, and Q3. From there, we can find the interquartile range, which will be Q3 minus Q1. If we know the interquartile range, we can be able to find the value of the outlier. The next is the standard deviation, which is the square root of the variance, is also used to measure the variability. Also, variance, which is the spread of distribution from the mean, is also used. Then outline will be the data on far end of the distributions, either very small or very big. We also have a normal distribution. Normal distribution is one of the perfect distribution because the mean, median, mode are equal to 1. They are the same. So 50% of the values are less than the mean and 50% of it greater than the mean. Now we can divide it into standard, which we have the normal standard deviation in the distribution, or z-score. Z-score helps us to find how the data is again deviate in the distribution. So for example, 68% of scores fall between 1 standard deviation above and below the mean. Then we have 95% falls between 2 standard deviation above or below the mean. Then 99.7% is 3 standard deviation, fall between 3 standard deviation above or below the mean. And this is a special rules for again normal distributions. So this is another normal distribution example graph. Sometimes we use the term bell-shaped curve. So the curve is like a bell shape. So now, if the mean, the media are not the same, then we are not going to have a normal distribution. So we have two options. Either the distribution will skew to the right or is skewed to the left. Now, if it's skewed to the left, we call it the negative distribution, which means the media is greater than the mean. Skewed to the right is a positive distribution, which means the mean is greater than the media. So many distributions are not normal. These distributions are skewed on the right, which is positive skewed, or on the left side, which is negative skewed. Now, the measure of central tendency, which is the mean media mode, are shifted in a skewed distribution. So, distribution negative skew is when the median is greater than the mean. Positive skew is when the mean is greater than the median. And normally, we also can calculate the skewness of any distribution. The skewness of any distribution will be the media of the distribution minus, mean of the distribution minus the median of the distribution divided by standard deviation of the distribution. Now, that's why we have the negative. We say if there's a negative skew, it means what? The median is greater than the mean because the formula is mean minus median, so the answer will be negative. Now, if the mean is greater than the median, the answer we get is positive. Always the skewness of any distribution, the value is between -3 to +3. And it's always the same formula. We have to find the difference of the mean and the median divided by the standard deviation. And also, that will take us to the next section where we have continuous and discrete variables. So in statistics, a discrete variable means, and the variable is based on counting. And also you have a finite value. Like example, give me a number of children. We can not say number of children is continuous value like a number of children is 2.33336. We cannot. Number of children will be either 1, 2, 3. So discrete variables is a categorical variable that only take on a whole numbers because it's based on counting. Then continuous variable can be a numerical variable that is take all possible units. So to remember this, the difference between discrete and continuous is that discrete is based on counting. We count 1, 2, 3. That's why we have no decimal value. By continuous variable is based on measurement. Example, my height, my weight can be 20.446 kilogram. The temperature of the weather or even the pressure of something, they are all continuous variables. So again, to be continuous, the difference between discrete and continuous. And also we say certain measures are more appropriate for certain variable type. Example, mean, media, and mode are appropriate with continuous variables. And then the discrete variable, only the mode, mean and media is not. So next we move to the bivariate analysis. When we say the bivariate analysis, we are trying to say that we want to analyze a data set that have two variables. So this is used to investigate the relationship between the two variables. So when I do bivariate analysis, it's like I'm trying to find the difference or if there's any relationship between two variables. These two variables are in the same data set, one data set. So let's say lung cancer and smoking. One data set, we have patients smoke, yes or no, yes or no. Lung cancer, yes or no. So we can find the relationship between the two. So we used to investigate the relationship between two variables, whether changes in one variable are reflected by changes in another variable. Here we say the correlation will determine the extent to which two quantitative variables approximate the linear relationship. Correlation, we use it to to know the degree of relationship between two variables or the degree of association. And normally the correlation value will be from -1 to +1. If it's -1 or close to -1, which means we have a decreasing relationship. When one variable increases, the other will decrease. Now, if we have a value that is close to +1 or is +1, then we have increasing relationship, which means when one variable increases, the other also will increase. So here we talk about a linear model for the regression. So a linear relationship would be a perfect relationship between two variables that will resembles a straight line. So in a linear relationship, the change in units of one variable is reflected in specific changes in the other variable. And this is very rare to find in a linear relationship in the research. Very rare. And also, a linear relationship is expressed as y equal to bs. Supposed to be bs plus c. So b will be the slope. B is the slope, or the unit by which y changes every time s changes. Then we will say maybe plus c. C will be our y-intercept. So this is an example of a bivariate data set. We have tomato plants and the amount paid. So here we are trying to find the relationship between tomato plants and the amount paid. Is it an increase or decreasing relationship? Increasing relationship means the more tomato plants we have, the more money will be paid, amount of money will be paid. So we can use the two variables here, find the correlation coefficient value. It should be from -1 to 1, and that will determine what kind of relationship we have here. So as we said earlier, correlations, the values are between -1 to +1. When the value is close to +1, it means we have increasing linear relationship. When it's close to 0, it means we don't have nothing. It's less likely the variables are correlated. There's no relationship. Then if it's -1, it indicates perfect negative correlation. Then +1 means positive correlation. So this is an example again for a positive relationship between father's height and son's height. You can see that based on the data, when father's height is increasing to the right, the son's height also is increasing to the top because it's y-axis. The father's height is x-axis. So the pattern of the dots here tells us we have increasing relationship between father's height and also son's height. And that will lead us to causation. We just talked about correlation. Correlation is finding the relationship between two variables, or we can say finding the association between two variables. But we are not finding the causation. Causation means we want to determine the cause of the outcome dependent. If it's based on the input variable or other variable. So we say correlation does not imply again causation. You just find an association between the variables. But because we may have a spurious relationship is when the correlation between two variables is affected by third variable. Normally we use the term confounding variable. So a very simple example here is we know that in the summer in Florida, shark attack increases. Many people get attacked by shark because the Florida beach start to get warm. When it's warm, the sharks, they come close to the front of the shore, the sea, where people are swimming. So often there will be shark attack between the shark and the human being. That is in summer. But at the same time in the summer, the sales of ice cream in Miami, Florida Beach goes up. So now can we say that there's a relationship between shark attack and sale of ice cream? But can we say that there's a causation? Of course, no. Because we cannot say that when a person gets attacked by shark, the first thing it's going to do is to go and buy ice cream. No. But there's a relationship or association between, implicit relationship between. So causation again means we want to know what normally causes the dependent variable. But we have to be careful because of the confounding variable or locking variable. So regression also is used for predicting. We have different types of regression from non-linear to linear. Here we are studying only linear. Non-linear can be logistic regression. It's a very good example. So yes, they say an imaginary line that will best represent the closest possible linear relationship between two variables, and is represented as y equal to a plus b is. A is our intercept of the y-axis, b is the slope. So a nonlinear relationship can be accessed using, for example, polynomial regression or logistic regression or careful linear regression. Most software applications provide all this type of regression. Also, we have a scatter plot, which is close to line plot. Again, we need the two variables bivariant relationship, because scatter plot means we have to have x and y axis of the plots. So the dot that represent the relationship between two quantitative variables. The y is the dependent variable, s is our independent variable. So independent variable will determine the dependent variable. So cigarette smoking and lung cancer, of course, independent variable here will be cigarette smoking, because lung cancer doesn't cause cigarette smoking. Rather, cigarette smoking causes lung cancer. So lung cancer will be our dependent variable, and smoking will be our independent variable. So next is the outline. We talk about outline data. These are data that is very small or very large, and it can have a significant problem with our data, especially if we are doing parametric testing. It can have a very big problem. That's why outlines and distort the research findings. So here we have to be sure to assess the presence of outlines. So we have our data set. We can find the quotas, Q1, Q3. Then from there, we can find the interquotas, which is Q3 minus Q1. Then from there, we can find the outline. Normally, outline for minimal value will be Q1 and minus 1.5 times interquota. Then the highest value of the outline will be Q3 plus 1.5 times the interquota. That's the difference between Q3 and Q1. So this will be our conclusion of this chapter. As you can see, again, we don't have enough time, but this chapter covers almost touches everything in statistics, except hypothesis testing and non-parametric tests. And again, the main goal of this chapter is to understand how to analyze quantitative data. So we use the parametric testing in statistics to analyze quantitative data. So again, wish everybody the best and thank you for your time. Also, we have an assignment that is due next week. And also we have quiz number 2 that cover chapter 9 and chapter 10 of the course textbook. Again, if you have any question, send an email to me or you can reach me at my cell phone number. Thank you.